Hello, my name is Jose Hernandez, and my partners in this project are.
Hi, my name is Parnia Islamizadeh.
Hi, my name is Loic Signe.
Our project advisor is Dr. Boscovich from the Electromechanical Systems Engineering Technology Department at Cal Poly Pomona. This is our project titled Hydraulic Robot Arm. The goal of this project was to design a low-cost, articulated robotic arm with 3 degrees of freedom. This arm would transmit power with the use of hydraulics pressurized by linear actuators and would be controlled with the use of specific hand gestures via a glove controller. The functional goal of this project is a simple pick and place of a 1 pound water bottle. The advantages of a hydraulic arm versus a traditional servo arm are smoother movements as hydraulic cylinders move in a smoother fashion compared to small servos. A hydraulic arm is also more robust as there is no need for gears or additional small components used for functional purposes. A hydraulic arm also has a greater power versus size ratio compared to servo powered arms. Finally, with regards to cost, our hydraulic cylinders were a lot cheaper in price compared to the small, high torque motors available in the market. With regards to the mechanical design of our project, it used 3 revolute joints that mimic human arm movements. The first joint has the ability to rotate 360 degrees. The second and third joint have the ability to rotate 90 degrees and an end effector with a simple static hook. In regards to the dimensional and material aspects of our arm uses aluminum flat bars with dimensions of 5 inches, 12 inches, and 10 inches in length. The thickness of these flat bars is a 1/4 inch. We also used number 8 2-inch stainless steel bolts and number 8 32 threads per inch coarse thread stainless steel nuts for our project. For our hydraulic cylinders, we use 60 milliliter and 100 milliliter plastic syringes. Finally, we used water as our hydraulic fluid. Now for the electrical components. For our system, we use two 10K potentiometers for feedback, 2 linear actuators, one with a 6-inch stroke length and the other with a 2-inch stroke length. For our base, we used a remote control rotary base. For our feedback processing, we used an Arduino Mega controller. For our glove controller, we used a LAF-VIN nano controller coupled with flex resistors, which is attached to our MC33926 motor driver, which is used to control the direction and displacement of our linear actuators.
Here is our SolidWorks mechanical model animation. And as you can see in this animation, we have flat bars, which is connected with the bolt and nuts. And as my partner mentioned, Jose mentioned, we have 2 syringes. One of them is the bottom one is 100 milliliter and the top one is 60 milliliter. We use 2 blocks for more support for the syringes. And as you can see, the motion of the arm is due to the linear motion of the syringes. And as they are extending and retracting, the arms goes up and down. Here, based on our SolidWorks design, in order to make sure that the arm is strong enough and is not going to break or deform due to the force that is being applied, we did the finite element analysis and we used ANSYS for doing this. We found the total deformation and equivalent stress. And due to the technical limitation of the software, we simplified the arm to be like this. And as you can see, this is for the total deformation. at the end of the last link, it's red, and that means we have most of the pressure is being applied over there. This is for the equivalent stress. It shows how the equivalent stress being applied to the arm. And over here, we show them, this is a mesh and the force being applied to the arm. Here is our DH parameter derivation, and we have three revolute joints. From joint 0 to 1, we have rotation of theta 1, and all other parameters are 0. And from joint 1 to 2, we have rotation of theta 2, and from joint 2 to 3, we have rotation of theta 3. From joint 1 to 2, we have a link twist of 90 degree, and the link length is L1. And from joint 2 to 3, we have link length of the L2. And all the rotations are about the z-axis. Here is the forward kinematic of forward kinematic calculation. So we have a transformation matrices from one joint to the next joint. And based on that matrices, we calculated the transformation from 0 to 1, which we call it A1, and 1 to 2, which is A2, and 2 to 3, which is A3. And based on the calculated matrices of A1, A2, A3, we found the product of those, and we found the transformation matrices from base to the last joint. Here's the inverse kinematic calculations, and based on that, we were able to do the simulation that you're going to see later on. We have the matrices that we already calculated by multiplying the inverse of A1 to the both side of the calculation. We were able to find the rotational angle of theta 1, and we follow the same method to find theta 2 and theta 3. Here's the simulation that we used Papillia sim for doing this simulation. And the target that we used is this cylindrical shape. And you can see the movement of the arm in this animation. This is a movement of the arm about the x-axis. About the x and z-axis. We are able to pick up and place the bottle of water, as you can see, based on the calculated inverse kinematics.
In this slide here, we have the block diagram of the feedback closed loop system of our hydraulic arm. It shows how the error in the system is being accounted to establish a more stable movement of the arm. Now in this video here, we have our robotic hydraulic arm that is metallic. Initially, we have decided that the end result of our hydraulic arm should be a metallic model. So here is a metallic model built by one of our partners in Florida. This model here showcases how the arm rotates around its own axis, as well as how the arm is obtaining, how the potentiometer on the arm are obtaining feedback from the movement of the arm. You can go ahead and play the video. So that is the Arduino Mega that is being used to create a reference between the potentiometer and the Arduino. So that is the rotation of the entire platform. And that is a 1 pound water bottle that is being picked up by our metallic model. And we can see as the hydraulic arm is moving, the potentiometer on the arm is generating a feedback based on the location of the arm. And we can see how the 1 pound water bottle is being moved to the area blue to the red area, and those are our feedback that are being generated through Arduino on this graph. So here is our glove controller. The reason why there's three different flexor on this specific glove controller is because initially we wanted our design to have 3 different linear actuators and 3 different syringes. But as we went by, we decided to make a more simple design. That is why in the upcoming videos, you will see how our glove controller only has 2 flex sensors for the movement of our 2 linear actuators and our 2 syringes. So here's another video showcasing how our glove controller is controlling the movement of the linear actuator, which in turn are controlling the movement of the syringe, creating the motion of the hydraulic arm. This model here is in wood because on this specific video, we wanted to showcase how we were able to control the linear actuator and our arm using flex sensors. Because of COVID restrictions, we couldn't meet. That is why we decided to split the work of our project within each other. So you can go ahead and play the video. So that is the glove controller in action. And that is the first flex resistor that is being activated. And that is the second flex resistor being activated. So when the second flex resistor is activated, the linear actuator is being extended, which in turn is pushing our fluid into the syringe on the bottom, creating the motion of the arm. And that is a 1 pound water bottle on the hook on our end effector. Awesome. So these are our works cited. So here is an article that we use for our project. We like to give a special thanks to our department or the College of Engineering or Department of Electromechanical System Engineering Technology. We like to thank them for all the resources the department has given us through our senior project. We also like to give a special thank to our senior project advisor, Dr. Boscovich, who's been there for us, who has given us a lot of feedback and a lot of guidance through the accomplishment of our senior project. And here's a LinkedIn. We will really appreciate to connect and network with other professionals in the area of our respected engineering fields. And we'd like to thank you finally for your time. We thank you for watching our presentation, and we wish you an amazing rest of your day, morning, or evening.